We have this conscious experience that we're moving our finger, right? And that this thing's happening as a consequence. So I want to explore that idea and its relevance for educational decision-making in my talk today. And I'll start off with some key claims. First off, I'll give you some illustrations of translating cognitive science research into the classroom. And in particular, talk about our work in developing the cognitive tutor technologies that are now in widespread use across the United States and in other places, including some parts of South America, as a matter of fact. A key theme that will run through my talk is how, in order to field science, we must overcome these intuitions that come from our conscious reflection. Our mind's conscious awareness of learning often obscures the tacit or implicit complexity of brain processes, and it can yield faulty educational decisions because we make our decisions based on the tip of the iceberg, which is our conscious awareness of our own thinking and learning processes. Most of thinking and learning's happening, as it were, below the surface. So we need data-driven science to better understand what's happening underneath here. One of many ways that I'll illustrate to collect such data is through educational technology use, which is becoming more and more pervasive. As students interact with technologies and even with paper, they leave a trail. They're like breadcrumbs in that old story. Those breadcrumbs can be used to make inferences about the learning paths that students take. And those are inferences that we make, but they're so important because we want to get at what's underneath the surface. To do this, I think, efficiently and effectively, we need to strive towards what Mark was pushing for, is to do more research in the context of schools. So I will talk about that. All the work I talk about today would not be possible without the help of many different funders and many of my collaborators over the years. I've listed just a few of them here. They include faculty, they include graduate students, postdocs, they include teachers and school administrators that they've worked with, and the many members of the LearnLab team that I've collaborated with. I'll do this in these parts. I'll give you some background on the Cognitive Tutor Algebra course that we developed and its success in scaling up into many classrooms. Talk a little bit about the challenges that we faced and how we're using those challenges as opportunities moving forward. I'll talk about our LearnLab Center and how we're trying to do some basic research on learning at scale in school classrooms. Part of that work is culminated in a theoretical framework called the Knowledge, Learning, and Instruction Framework, or the CLE framework, and I'll outline that particularly in connection to this notion of our conscious awareness as opposed to our implicit brain thinking processes. And I'll illustrate how we can close this loop here, this continuous feedback loop of designing new forms of instruction, trying them out in the classroom, collecting data on their use, making new discoveries, and using those discoveries to redesign. This is a virtuous cycle, if you will, of improvement that I want to emphasize. So let me start with some background on the Cognitive Tutor Algebra. It's a great example of the real-world impact of cognitive science research. It's based on cognitive science theory, in particular John Anderson's theory, which he calls ACT-R. And in particular, we use that theory to develop computer-based cognitive models of student learning. And I'll illustrate what I mean by that technical term, cognitive models, in a moment. We've had great success, as I mentioned, in disseminating and also in demonstrating improvements on student learning, which I will talk about. So key to this approach is combining a research base and an interaction with practitioners in the field, math educators, mathematics teachers, the standards, and so forth, and pursuing this iterative process of designing not just technology, but text materials, teacher professional development training, as well as the technology, deploying that, paying particular attention to the social context of use of those technologies, collecting lots of data, process data, outcome data, qualitative and quantitative data, and using that to make discoveries that then can feed into redesigns. So let me start by talking a bit about the practice space, and had a great opportunity of working with a very talented teacher, Bill Hadley, who he came into this collaboration with an idea that we don't want another algebra course where students check their common sense at the door. He wanted a course where students understood the relevance of algebra to thinking and reasoning in the real world. And as a consequence, this course has lots of problems intended to engage student intuition and interest. Problems about healthcare, about extinction, about smoking risks, even about the importance of math education for future employment. In that context, we've built, as I said, text materials and teacher professional development, but I'll emphasize the technology. This cognitive tutor technology has, in a number of the units, students reading pretty rich problem situations like the ones I illustrated. This one's about 2 different cellular phone plans that students are asked to compare. And they do that by working through various representational tools. This one's like a spreadsheet. And the students are labeling the quantities involved, the time, the units involved, perhaps providing symbolic algebra notation or variables for that. Here's one of the 2 plans, the current plan that's being described. And here's a student entry that has been flagged by the tutor as missing something. It's missing the fixed cost here. So the interactive tutor is following every step that the student is making in this pretty rich and complex problem, and it is able to provide in-context instruction to help students get over some of the difficulties they may experience. This instruction comes only to students as they need it, and not all students then get it. Some can proceed at their own pace. They're challenged with harder problems like when do these 2 plans intersect, and they can always ask for hints about what to do to make progress. So this is later in this problem where they're suggested they might write an equation to find the number of minutes involved. So popping back up to the full screen here, we can see that students not only build this table, they are using an equation solving tool. Sometimes they get practice on these tools in isolation to work up their skills on each one. They're also drawing a graph here and finding the intersection point, labeling the graph and so forth. And everything they do is being tracked with the underlying concepts and skills that are being applied as they solve this problem. And this is used to select future activities and tasks to focus and individualize the instruction on just what each student needs. So that gives you a sense of the practice space and what the tutors look like. Let me say a little bit about what's happening underneath the hood in terms of the research. What's the engine that drives this? And it's both some technology, some advanced artificial intelligence technology, and some data collection, some cognitive psychology research. Let me start with the underlying technology. We use cognitive theory to individualize instruction, and a key element of this is this notion of a cognitive model. That's a system or an expression of how students can solve problems in various ways. And I have a simple example here of a student who's come to this point in a problem somehow, it doesn't matter how. The system has encoded rules for different ways to make progress here, and 2 of these are reasonable things to do, and 1 is a typical student error of not multiplying the 3 by the -5. So this cognitive model is written so as to help make predictions like this, be able to generate next steps in all the possible situations students can get in. And that's a technical challenge, but it's one that has real power because it allows the system to follow students through their individual approach to a problem and provide context-sensitive instruction. Attached to each of these rules, or production rules as they're called more formally, are hints that get generated, and the specific context of the problem are inserted into these hint templates. Or in this case, this is a bug message to indicate an incorrect move that the student has done here. The second key technology is called knowledge tracing, and that works across activities. Model tracing works within a complex problem. Knowledge tracing works from one task to another. It assesses students' knowledge growth. What's the chance that this student knows this rule? And it uses that to individualize the activity selection and pacing. It's what drives this skill bars that we saw earlier. And when this gets to 95% estimate, they're checked off. And when all are checked off, students move on to the next unit. Before that, the skills they're having more trouble with lead to more problems along those lines. So the key to success here is building a model that really does capture the way students think. And I think we, in our conscious reflections, sometimes we underestimate the complexities there. So I want to illustrate how we use data to dig into some of those complexities. And I'll do so through another quiz, which is 3 items from an actual set of quizzes we gave in the classroom. I'd like you to reflect on, for a moment on which of these 3 problem types is the hardest for a beginning algebra student. So I'll show you data in a moment, which is from about 7 months into a first-year algebra course. So notice all these problems have the same numbers. They all have the same answer. They're presented in, thank you, was requested to read the problems for translation purposes. So the first story problem says, as a waiter, Ted gets $6 per hour. One night he made $66 in tips and earned a total of $81.90. How many hours did Ted work? The word problem has no problem situation, but it's in English. Starting with some number, if I multiply it by 6 and then add 66, I get 8190. What number did I start with? And the last one's an equation, x times 6 plus 66 equals 8190. So what are your thoughts? Who thinks the story problem is going to be the most difficult? I'm going to show you percent correct rate of students in a moment. We got a couple votes for story problem. How about the word problem? More votes for the word problem. How about got a number of votes for equation? Interesting. I'd be curious to hear what your reasoning is here, but maybe we can't do that at the moment. Yeah? Does anybody want to give me a reason? What did... Shh. Can they... Way back there. Yeah, it would have to be in the last row, wouldn't it?
Well, I would think the story problem would be the easiest because it's contextual and it's applied to real life. And it's a story.
You think it would be the easiest?
Yes.
Which would be the hardest?
Well, I'm an English teacher, so math is horrible for me. So for myself, the equation, I think, would be the hardest.
You think the equation would be hardest? Interesting. We got someone's vigorously saying no. I have to say that I'll show you some teacher survey data in a moment. I went into this study wondering why story problems are so hard and whether I could understand what are the components of the story problem that make them hard by breaking them down into what felt to me like simpler problems. I was using my conscious reflection on my own thinking and learning to make that inference, as you were, but maybe we were different students. Here's the data, and we've replicated this a number of times now. What we found, at least to my surprise, and maybe to about 2/3 of you, that the students had the most trouble. They were only 42% correct with those equations, and they did better on the story and word problems. And when we looked at their solutions, we found that they're not solving those story and word problems by translating them to the equations, otherwise this result wouldn't make any sense. That was the logic I had. But they have various informal and pretty clever ways of solving these problems without using the equation. When we looked at the equation solutions, we saw signs of essentially lack of comprehension. It looked to us, in essence, that for many students this was like a foreign language, the foreign language of algebra, and they were having trouble reading it. When we surveyed math educators and teachers on this, they were typically quite unlikely to say that the equation would be the hardest. And interestingly, the high school teachers that teach this content were the least likely to get it right. Their expertise, as mine, got in the way. The equation's easy for me, it's easy for them. They thought it would be easy for their students. Their conscious reflection on their experience actually missed out on probably was a lot of work that their brain had done over the years of learning algebra to acquire that knowledge. So we can go back to this. Oh, and by the way, studies like this and I could give you more details, but we ran this study as a quiz that took maybe 15 minutes in the classroom. And there's some subtleties of using multiple forms. You can't ask the same question with the same answer on the same quiz form. But apart from that, it's pretty easy to implement in the classroom. And I'd be happy to talk with teachers about how to do that. Let's reflect then on this mind versus brain thing. Our minds tell us, well, gee, that story problem is longer. And we saw in written explanations from teachers some of these things. You have to read the story problem as if somehow the equation jumps into your head automatically. And the equation shows you what to do. It does if you're an expert. But what's really happening with the brain over time is algebra is a language. It has, amongst other things, a grammar. And that grammar is learned by the brain implicitly with experience. And that takes real time, but it's often not recognized by the experts who acquire it. So all of this is kind of investigation is important because remember that cognitive model, that was the key driver for all the forms of instruction in this online tutor, and I would submit is a real guide to instruction more broadly. If we know more about the way students really think, we can select better learning activities, we can provide better instruction. Here, for instance, we can help students see how what they already know informally of solving those story problems and word problems, how that can help them understand how to solve an equation. And in the context of these tutors, we can change the way the adaptation works so we better adapt to the real needs of students. So this kind of work has led to the Cognitive Tutor Algebra course, and I'm not saying much about the text materials and teacher professional development, but we paid a lot of attention to the design of those as well. And many field studies have been done. This is an early one that I did comparing end-of-course outcomes of students in the Cognitive Tutor Algebra course with students in a traditional algebra course on various standardized tests, as well as some tests we designed to really get at what we thought was most important, real-world problem solving and conceptual understanding of the different mathematical representations of algebraic functions. Many such studies have been done by others. Some have come out, most have come out with positive results, some have not. And there's a whole interesting, rich history there I could tell you about. What I do want to do, though, is step back a bit and tell you a little bit about our early scale-up. So we started this in the early 90s, and this graph shows the number of schools that got involved over the first 7 years. And what we observed is how it was important to have a full solution, that just having technology only in the classroom, particularly at this time, was difficult for teachers to make decisions about when they should use it and how they should use it. So having it integrated in a full curriculum really helped in adoption. We had achievement gains that suggested it was worth adopting. We really paid attention to classroom impact. We had teachers involved with our development, which was not only important in developing a good set of materials, but it was also important in terms of disseminating them, because Bill Hadley and I would go to schools, and I could say exactly what Bill said, but he was the teacher, and teachers understood his experiences and believed them more than they did researchers. To get sustained use, it was really important that we sought support not only from administrators, but the teachers using it. We did lots of teacher workshops, focused a lot on ongoing technical and curriculum support, had focus groups, and even parent algebra nights to help parents in districts feel more comfortable about their kids using technology. And in the first early years, all of our dissemination was grant supported, but in order to scale up, we started asking for support costs from schools. And that then led to, in 1998, we spun off a company. We were in 75 schools there. It's called Carnegie Learning. It still exists today, and about more than 500,000 students a year are using this about 2 days a week in more than 2,500 schools across the US, as I said earlier. So looking back on this, in some sense, it was a real success in dissemination and applying cognitive science to the real world. But I don't feel like we were done, and I'll give you a couple of the key reasons for that. One is, if you look closely at the absolute achievement on those bar charts, and this was in pretty tough urban school, the achievement is still far from ideal. There's lots of room for improvement. Another thing, though, is so many of our design decisions that we made were not guided by science, but they were based on discussions and arguments we had in the design team and our intuitions. So what we began to recognize is this technology could be used in a way to further this continuous improvement, to collect more data, to make more discoveries, and to influence the design going forward. And this experience and experience of other colleagues of mine that was similar led to the formation of the Learn Lab, or the Pittsburgh Science of Learning Center. We wanted to really address this chasm between basic science of cognition and educational practice. There's too big of a gap, we observed, between what's known and what's happening in the world, and in both directions. Scientists not appreciating how much practitioners actually know in one direction, not enough use of some good ideas in science in educational practice. So the Learn Lab is one of these infrastructures that we heard suggested yesterday would be a good idea to help bridge this chasm. Mark talked about infrastructures yesterday. In the Learn Lab, we have mechanisms to support collaborations between researchers and teachers to run experiments in schools. And in particular, we use the educational technology as a scientific instrument, think like a telescope or a microscope, that's embedded in educational practice, in real courses, particularly at the high school, middle school, and college levels, that we can use to understand what's really going on. And our purpose, our general purpose, was to identify what conditions cause robust student learning that transfers to new situations, that lasts a long time, that helps them learn new things, that even leaves a desire to learn new things. Robust student learning was our focus. So the infrastructure involved technology-based blended courses, so they had a human teacher element as well, in a variety of domains, online statistics course, there's an English second language course, we have educational games online, this one's a fraction number line tutor, that are in wide use such that we can do what we call basic research at scale. And part of that involves, instead of researchers negotiating with schools individually, the Learn Lab's a central place where they can come and work with us to work in one of the sites that we've developed that are using any of these courses. It makes it easier on both sides to coordinate those activities. And as a consequence, we've run what we call in vivo experiments in these courses, about one per semester in about 6 courses every year, for a total of about 280 in vivo experiments. And I'll give you some examples of these later on. We've also collected a vast amount of data that's available. I think we have the world's largest open and free data repository of educational technology data sets. As I mentioned, there's a lot of different courses in educational technologies in which we've done this work, and we've leveraged that for a lot of insights. I'm going to focus on work in math, but if you have questions about work in other areas, I'd be happy to address them later. A key output of our work has been this knowledge, learning, and instruction framework. A prime publication appeared last year in the Cognitive Science Journal, and I wanted to give a high-level view of some of the key distinctions of critical elements of learning. And this diagram helps illustrate how we want to be careful when we're talking about the difference between instruction and learning, and the outcomes, the mental outcomes of learning, and then how we observe and assessment those outcomes. And assessments ideally happen much later than the learning to see whether the knowledge that was acquired has been learned in a robust way. So this stuff happens in the brain. It's unobservable. This stuff we can observe our only modes of instruction going on here. So, yes, reminded to read, thank you. Instructional events here, examples include explanation, practice, some text materials, teacher-student discussion. Assessment events are things like questions and feedback, or a step in an intelligent tutoring system. These are also instructional events because there is feedback. Exams or a belief survey are forms of assessment that don't involve instruction. Learning events and knowledge components interact in that as we learn, we accumulate knowledge, and we mean this very broadly to include skills and metacognitive skills and learning to learn, and those influence future learning. So going back to this diagram, what we see above the surface are the things we're doing and the data we're collecting from our assessments, and we're making inferences about what's going on in the brain in terms of learning processes and knowledge components. So why do we want to be careful about making this distinction between what we can and cannot observe about learning? So much of learning is tacit, it's nonverbal, it's hidden from view, and over again, cognitive neuroscience research as well as cognitive psychology research has revealed how much of this is happening. So if we use data-based discovery to dig into what's going on here, we can come up with new insights, and they're often about details of learning, and that's why I think it's so important to be doing this with teachers in the classroom, because it's the details that really matter on a day-to-day basis for your effectiveness as a teacher. And of course, you want to use those insights to design better instruction. So let me give you another reflection on this idea of what you're consciously aware of. So for some of you, not all of you, you've had lots of experience with the English language. You might substitute your own language here. You might say in that case that you know English, but do you really know what you know? For instance, if you're a first language speaker, do you know why the is in front of English here, but it's not in front of English here? It would sound weird to say you've had lots of experience with English language, or you might say you know the English. It sounds wrong, but I think unless you're a linguist, or maybe a second language learner, it would be difficult for you to explain how you know what you know. More generally, if you think about a young child learning language, they're able to learn language before they have a language to use to learn. So somehow our brain has these capabilities to learn without language. And particularly, we have lots of pattern learning, pattern abstraction processes. We learn grammatical structures in language without explicit instruction. So a question for you is whether these processes that are so important early in life, do they continue to be relevant in other forms of learning? Say even in learning mathematics, like learning high school algebra. So consider here a crucial math skill, which is modeling real-world story problems in the language of math, like in an algebra equation. This is so important because this is one of the things a computer can't do. And if you can do this and use computer tools, you're a really powerful thinker and learner of mathematics. So we did a series of studies, again in this framework of looking for difficulty factors in quizzes or assessments. This one about symbolic modeling. So a problem like this one is Anne's in a rowboat on a lake. She is 800 yards from the dock. She then rows for m minutes back towards the dock. Anne rows at a speed of 80 yards per minute. Write an expression for Anne's distance from the dock. And what we're looking for is an algebraic expression like this, 800 minus 40m. And in this sample of 8th grade students in the US, students have trouble with these kinds of problems. On these kinds of problems, they were only 40% correct. Now, you might reflect on why this is hard for students. Any ideas why these problems are hard? Somebody want to shout out a thought? What?
Converting language to different sorts of symbols. It's a different structure of communication.
The symbols are a different structure of communication? Yeah, that's a very good hypothesis. Let me come back to that one. What I often hear is people say, teachers, that reading the story problems is difficult. So one of the things we tried is, what if we give a hint to students about to make the reading easier? In particular, there's no mathematical operators in here. You know, you have to figure out that subtraction's involved, but it doesn't say subtraction. You have to figure out that multiplication is involved, but it doesn't say multiplication. So what if we give a very similar problem that has these hints on, that makes it very clear that to get Anne's distance from the dock, it's equal to the distance she started away from the dock minus the number of yards she rowed back from the dock. And this one gives us the multiplication relationship. How much easier will that be? If comprehension's a real sticking point, we should see a big increase or a reasonable increase in the rate of success here. Here's what we found. A very small increase in success. It doesn't seem like comprehension is hard. Here's another piece of evidence. If we simply take the same problem and replace the m minutes here by 3 minutes, and instead of asking them to write a symbolic model, we ask, what's the numerical answer? We find that the problem gets dramatically easier. They can read these problems and they can solve them. What's hard is, as the person in the back indicated, it seems, is the output form. It's the algebraic language. It's translating. You could think of this as translating English to, I don't know, let's say Spanish or Greek, right? The hard part, if you know English, is the language you're translating to. So to investigate that further, we thought, well, maybe part of the hard part is learning the grammar that an expression like 40M can be inside of another expression. So if we break this into two similar problems and ask, what's the overall performance to get both of these pieces right? You can't just get one right, you have to get them both right. It's pretty equivalent to that on the surface, but it's a dramatically different performance that's much easier to do. So what we were left with is that learning the grammar of putting one expression inside of another was a key sticking point for students. So this, again, is something that we're not necessarily consciously aware that we're learning, but the data reveals how critical it is. So what do we do with this information? Oh yeah, reminder, you can run experiments like this in your classroom. You can have hypotheses about what kinds of scaffolds or prompts will help students and put them into quizzes and see if they really do. So we had this thought that maybe we could practice students with the grammar to help them learn how to produce better expressions in the second language of algebra. And it was a very simple idea. We would give practice on problems like this, which seem to have nothing to do with story problems on the surface. Substitute 40x for y in 800 minus y, or substitute 972 plus b for d in d divided by 5. And if you know your math, this one's going to involve adding parentheses, right? So some subtleties here, but we're isolating that key gap that our data indicated was problematic. And the result is when we do that and compare students who are getting practice on story problems, we actually get better results by having them practice on these grammatical exercises, if you will. So I wanted to give one more sense of the way we tackle this problem of understanding what's happening under the surface, and that's through computational models of learning. I think we heard a little bit about computational models of brain function yesterday. Our focus here is at a higher level at problem solving and thinking and how to learn how to problem solve. These models are powerful because they help us make inferences from those breadcrumbs of learning events that we can observe to the underlying learning processes that we can't. It helps us make sense of complex brain processes of what's happening underneath the surface. So we have this system we call SimStudent, which is a computational model. It's a computer-based AI system that learns like students do. And in particular, one of its ways of learning is by observing the structure of the world it's in, like an algebra world in one of our tutors. And just by exposure to expressions like that, and by noticing how elements co-occur, it's building chunks, if you will, that then become part of a grammar, and those chunks build up, and that is the way we hypothesize that young children are able to learn, and there is other research that indicates this, are able to learn grammars from experience. It's largely based on the statistics of co-occurrence of words, or in this case, algebraic symbols. And this model makes predictions about what's going to be hard for students in learning algebra. So let me give you 4 examples of what often happens at the end of a solving equation, where students are down to steps like this, and they have to figure out what to do next, like divide 2 on both sides of this equation. So which of these do you think is the hardest for students to do? I saw the bottom one. I heard somebody say the second. 2? Oh. Here we go. The whole time you can't see. Lots of people say the 4th one. What SimStudent had most trouble with is the 3rd one. And if you think about this at a perceptual level, what you learn by experience is a coefficient's a number in front of a variable. But there's no number here. You have to learn a different grammar rule for this. And when we look at actual student data, and we did this actually afterwards, SimStudent had this experience, made this prediction. Huge difference in error rate between these 3 problems and that one. So a nice prediction from the computational model. So I'm all in favor of doing studies like this in the classroom to collect data, but we also can be developing better and better theory that can make predictions ahead of time about what's hard for students. So the last thing I wanted to do here is illustrate a study that did a complete close-the-loop process here. From an existing system that had been deployed, data we collected from it, a new discovery, a redesign, and then an experiment that compares the redesigned part of a tutor, it's in geometry, to the original system, changing just a very little bit of the system. And part of this is inspired by practice guides that the U.S. Department of Education has put together. This one's called Organizing Instruction and Study to Improve Student Learning. And there's a long list of authors on here. I was actually one of these authors. And there are 7 recommendations. I'm showing 2 of them here. And in particular, I wanted to focus on this one, use quizzing to promote learning. If you know the literature on this, this is called the testing effect. Or another way to think about this is practice makes perfect, or practice helps to facilitate long-term memory of what you've acquired, or robust, one of the features of robust learning. But it leaves open the question, particularly in these domains where you're trying to acquire general skills, beyond just facts, of what is it that should be practiced. So that's what we were that's one of the things we can explore in all this data we have from educational technologies. And one of the ways we do it is by looking at learning curve data. So on the x-axis here, I have the number of times a student has had an opportunity to practice something, like an area formula in geometry, like finding the area of a rectangle. And here is averaged across all the students who've had, say, 1 opportunity. What's their error rate? After 2 opportunities, what's their error rate? So a learning curve should curve down, right? The error rate should go down with practice. So if we just ignore the details of this domain and just count every activity they did over time and plot that curve, it doesn't look very curvy. The details matter. So what's going on here? Why isn't this going on? Well, new topics are being introduced, if you will, and I want to get beyond just the notion of topic, but like trapezoid area is happening about here, and it's quite a bit harder than rectangle area. So the shape of the learning curve provides a guide to what's going on underneath, what's hard for students. So this is actually a curve from our data shop where I said we have almost 400 data sets from a variety of different areas. And there's all kinds of tools here for visualizing these curves and for doing statistical analyses, like if you know variations on item response theory and logistic regression. If we take this same data and instead of thinking of it as though there were one skill, like you're exercising your geometry muscle, we think about individual components of skill or concepts, and we decompose, in this case, into 12 different possible area concepts or skills. Same data is drawn over again, but now we're counting the opportunity to do each one of these things. Now we get a smooth curve. The red line's the same data, the blue lines is a statistical model that predicts. By the way, some of the students who are doing well in the tutor are graduating and moving on. So the reason this line goes up a bit is that there are more of the struggling students left at the tail of this curve. And the statistical model also is able to account for that. But the thing I wanted to focus on is how the smoothness of a learning curve guides us to what the underlying thinking components are. And what you can do in DataShop is not only look at the overall curve, so this is averaged over all of these components, you can look at curves for each one of the components. So circle area, this is from a reasonably small sample. I think it was about 60 students. It's a little bumpy, but it's clearly going down. And this trapezoid area is definitely harder, but also going down in error rate. One thing you can quickly see, and I see this over and over in these data sets, is oftentimes the course is practicing stuff that starts off easy and remains easy, yet we're doing it a lot, right? We're wasting students' time with simple things. And a simple way you can redesign the course, if it were a textbook, or in this case, an educational technology, is to reduce those activities so students are spending more time on the things that are hard. And we've done one of these in vivo experiments where we did just that, and we showed we saved students about 25% of their time, which over a school year is a huge amount that they could be doing other things with. The other thing you can see is curves like this, which are really bumpy and flat, and this indicates that our notion of what that concept or skill is, we've got it wrong. It's more complex than we think. And let me illustrate that here. So what we have here is two very similar problems. They're very standard problems, actually on standardized tests, at least in the United States. One's where you can't just apply a formula off the shelf, a regular formula, but you have to combine formulas. So this is saying if I cut the end of this can out of this metal square, how much area is left over? And students work on this problem in a table here where this column's the radius of the can, and this is the length of the side of the square, and here's the area of the leftover scrap metal. And for each question, which is down below here, they're given a number for the radius and a number for the side of the square, and they have to compute this. This is essentially the same problem. All of these steps here, these three and this one, are labeled the same way in the current model. They're all what we call composed by addition. But notice that that there is some scaffolding going on in the problem below here. Let me first say that when we look at the data, this step is hard, this one's sort of medium, steps like this, and these two are really easy, low error rates. So that's what makes that curve bumpy. And when we think about it some more, what the reason that, so here's the question. It's the same exact math that they're executing in all of these steps, but the difficulty being experienced is very different. The difference is in the planning that's needed. In the case here, they need to come up with the idea that in order to find this irregular shape, they're going to have to find the area of the circle, find the area of the square, and subtract them. Here, they've already figured it out, and for the next two questions, all they're really doing is arithmetic, and that's why that's so easy. Here, in this problem, this notion of scaffolding, giving students some support to help them with hard problems, is being used. Here we've prompted them with first find the area of the square and find the area of the circle and then find the scrap metal. And when we provide that scaffolding, performance goes up, but we're not exercising those planning skills when we do that. We've taken that away from the need for students to do that. So this insight led, by the way, when we add those skills to the statistical model, we get better fits of the data, and that's part of the doing good science. But we can then say, well, what does that tell us about redesigning the tutor? First of all, this adaptive problem selection shouldn't just have one skill, but really have three. It really needs to track the planning separately from the simple subtraction or the cases when students are doing problems with scaffolding. We also need to sequence the problem so students are starting off with the scaffolding and it's being faded as they're gaining more experience. And the last thing we did was create a new kind of problem we didn't have before in the tutor, which isolates this tough skill of planning. And it looks something like this, where they're given another problem. This time they're adding the area of a square and an area of a trapezoid if they know what they're doing. And we don't ask them to find the area. We ask them, what's the plan you're going to use? And they're going to pick a plan from this menu of plans. And the correct one in this one is add the area of the square SQRE to the area of QUAR as follows. So it's a short, quick problem, but gets at the essence of what they need to learn. So here's one of these in vivo experiments embedded in the classroom. So in vivo means live, right? Live in the context of a real course. We are comparing two different tutor versions, the one that existed before that had just those scaffolded problems, and the new version that had these unscaffolded problems with the gradual fading of the scaffolding support, and the problems that involve isolating steps in the tutor. For planning skills. So we had 103 high school students that were randomly assigned to one of these two conditions. We had a pre-test, a post-test, and we also tracked the time it took students to get to mastery. And what we found is that the redesigned students learned better and faster. They're much more efficient in their learning, taking only about 20 minutes, whereas in the original tutor, the students on average took about 30 minutes to master this unit of instruction. And interestingly, if we look at where they're spending the time, these key planning steps are actually getting more attention in a less amount of overall time in the treatment, just what we wanted. We're really helping them focus on what's hardest. And when we look at the results and particularly break down the results of the treatment for these composition problems, they do substantially better with little sacrifice for the more basic skills. So here's a close-the-loop experiment. We started with a system, we collected data, we noticed the detail that we can improve, we improved it, compared it against the original, and got better results, both in terms of time and in terms of enhancing learning skills. So let me say a few things in summary. I'm going to point you to another event that you might want to go to today that's related, and then make a concluding statement or two. I've discussed some examples of using cognitive science to bring ideas from cognitive science to the classroom in a way that really scales, that's really been disseminated widely. I've emphasized how in this work we've really had to work hard to get past the designer's sense of intuition that's driven by their conscious awareness of learning, and that often gets in the way of understanding what's really happening in the learning process in the brain. That's this notion that most of what we're learning is below the surface. We use data-driven science to get at it. In the last example, which is one of many, it involved collecting lots of data from educational technology uses to then make inferences from their trails of experience about what's going on in that learning process. And I also illustrated how we're able to do basic research in schools. There are other infrastructures for doing school-based research, and one of them's the Strategic Education Research Partnership, or SERP. And Juliana Parlagov, her name's as hard as mine. She has a session coming up called Math Education that I invite you to go to. And that partnership I've been involved with. I actually have done some very interesting studies working with school administrators and teachers who define the problems. The researchers don't define the problems. The school professionals provide the problems, and the researchers work with them to find ways to see if they can solve those problems of practice. So I'd highly recommend that session. So in conclusion, much of our learning is hidden from our view. We need to do research in schools to make data-based discoveries and to test the insights and designs that are inspired by those discoveries and lead to new practices. Some of this research teachers can do on their own, and certainly with collaboration with researchers. So thank you very much.
Hello? Oh, sorry. That was absolutely wonderful, and it was actually giving us two really big things to think about, right? We've got this whole process of how to do educational research in the classroom, which I hope everybody is going to be more conscientious of how to do an application in that sense, but also the general content related to math and how each of these huge skills really have so many subset skills or sub-skills that are pieces of that I hope everybody's taking away from that. I'm afraid I have to apologize on our part. We are going to take the coffee break 10 minutes later because of a preparation challenge we have, which is great though, because it's going to give us some more time for questions. And so I'd really like you guys to take some time now to actually pose a lot of good, high-quality questions, and so that Ken can actually help you feel even more inspired to do some of this application in your classroom.
Similar
I know that you had
with
wanted
physics.
to ask something.
I see here you wrote, did science and language. Did you do anything with physics?
The question is, have we done anything in physics?
Yeah.
We've done things in lots of domains. Physics is actually one of them. I'll recommend to you my collaborator, Kurt Van Lane, who's got an intelligent tutoring system for physics that he's employed in classes like this. In fact, one of our core, what we called Learn Lab courses, was a physics course, and it was at the key site was at the Naval Academy in the United States, and they've used this physics tutor for many years.
One more question. When you are explaining all these things, you have the answers written in form of ABC, but is there a choice for the students to write their own answers? The answers may not fit into the categories that you have. Is that a restriction on the students about their cognitive reasoning?
Well, did you mean multiple choice questions when you said they're in ABC form? Well, in matter of fact, they're rarely multiple choice. One example I gave later in my talk, which was about this planning thing, those were multiple choice questions, but they're hardly ever multiple choice questions. So in this image, students are filling in this table, and there's lots of ways to write this mathematical expression, for instance. And every one of those, the system has to be able to follow. When students are solving this equation, there are many different strategies that they can take to solve that problem. In physics, the challenge is even harder, there's a lot of intelligence in this intelligent tutor to be able to track those alternative strategies. And that's really what makes them intelligent tutors and makes them different than other forms of technology that are out there, becoming very popular, for instance, in the MOOCs we see these days, where there's a question and there's an answer, and that's that. Here you see a lot of working out of the strategies, and the intelligent tutor has to be able to follow those well, and it's an engineering challenge to do that. Oh yes, why they do what they do is very important, and one of the principles in that practice guide I showed you two of is this principle of self-explanation, which is having students explain, rather than teachers explain, why they make steps. And one of the many in Vivo experiments that we've done is to compare a tutor where students don't explain their steps to ones where they do. And we find we get much better understanding and transfer when students are prompted to explain. Though there have been studies like that in physics as well. Actually, and in other things like learning about French culture. I could give an example if you wanted to see.
Thank you for such an interesting talk here, over here to your right. I was wondering, concerning your traditional versus cognitive tutorial approach, whether you also gathered any more ecological measures, such as how they do in school in general, or standardized tests, or whether they go on to do honors or AP math, or? Not in that particular study, but in other studies we've done some of those things. And that's a great opportunity for working with schools where that data may be naturally collected as as part of the school. So, I'm very much with Mark in envisioning a future where schools and even colleges that some of us are in think of research as part of the way they do business, right? And they're collecting that data and using it in this kind of cycle that I illustrated to improve practices. But there's certainly more of that we could do. And it would be great if we got cooperation with school sites to collect the data that's already there.
I have a comment on what you're talking about, translating normal English language into mathematical formulas. As an English teacher, I can also notice that the way that you use, the way mathematicians write stories often uses English words in a way that normal people don't. So
yes.
Maybe, like X per Y or substitute. So maybe you need to do a little bit of testing on whether that grammar and those expressions are also understood in mathematical ways.
Yeah, it's a good question. How much of the formal terminology in math is necessary, or is it in fact getting in the way of the learning process? Actually, recently saw a paper in accounting where the big difference they saw in a study like this was the problems that were in everyday language were solved much more accurately than the ones that used accounting language. The response I've heard to that is, well, if you go out into the world of accounting, you need to know the language. I'm not sure I'm satisfied. I'm kind of with you that, why use jargon when you don't have to? But
I'm not saying that. I think you need to teach the jargon. Sorry.
Oh, yes.
You need to have some little teaching,
yeah.
like what is X per Y?
Yeah. So one exception to this comprehension, being easy, the word discount, for instance, packs a real punch. It's not one operator. It's subtracting a ratio product. It's really like 3 operations in one word. And that's not a word that you might know in a kind of everyday sense, but to translate it into a mathematical sense, there should be isolated practice on just that. But that's kind of the program of research I'm suggesting. Not all words are hard. You have to understand what are the things that are real sticking points for students, and then you can adapt your instruction to those.
Okay, we're going to take just one more question, and then Claudia is going to give us instructions about what's going to happen next, okay?
Thank you. Ken, I did not hear any references to speed and automaticity about getting to the right answers. And so much of this lies on the ease, fluency of producing stuff, so that you actually can spend the time and figure these things out. And I wonder, of course, in the US, they've gotten very much away from that, but we can't get away from the limitations of working memory on this.
Yeah, it's so important, and it is reflected indirectly in these error rate learning curves. You can change the output of these curves to be the time, and those go down too with practice, right? And it is critical if you're going to use these skills in a subsequent course, you need to have the cognitive headroom to learn the new stuff. You have to be fluent. You have to be able to do the prior stuff quickly. But what's reflected even in these error rate curves is it takes practice. The brain is plastic, but plastic isn't water. It isn't glue, right? It takes time to shape and mold. And I'm amazed when I look at the rate of learning we see across all these courses. To put it in technical terms, it's about 0.1 of a log odds or logit per opportunity. It takes about 40 opportunities for each one of these components for a student to master it. And that is largely, it's about accuracy, but it's also about fluency.
How about then putting in the tutor, or why have you not done it, mindless repetitions of meaningless stuff? For example, all those equations. As I learned in the world back then, where they were teaching mindlessly these things, you need to move components from the negative to the positive side, you stack them up and you add them up. You don't know what it means, but you get a product. That is an automaticity part. Is there any utility in putting such exercises so that reaction time will drop further down, and then you can have the cognitive headroom?
Yeah, well, I guess my view on that is reflected in a sports analogy. If I want to get good at tennis or at algebra, I need to play the big game. And the big game in algebra is modeling problem situations to make useful inferences. But I also need to get good at my serve, at my overhand serve. So I have to practice that in isolation. So some of the units in this tutor are focusing on those skills, like solving equations, and they just practice those skills, and there's not a problem context. And I think there's a temptation to say, understanding first or fluency first. And I think the right answer is that they're heavily interactive. You want to get a sense of context and purpose, but you want to be developing fluency, and there's probably the best way to go, and we have some studies along these lines, is a back and forth between the two.
Thank you very much, Ken.
Thank
Another
you.
applause, please. Thank you.